Today we will study the phenomena of boundary layer. Boundary layer is a consequence of the no-slip condition. Because of the no-slip condition, a very thin layer of fluid sticks to the surface, the stationary surface, when in contact with a flowing medium, when the surface is in contact with a flowing medium. So this is the interface of where the fluid and structure interacts with each other. So outside the boundary layer the mechanism is different, and on the inside of the boundary layer there is a different mechanism. So let's start with the Navier-Stokes equation. The Navier-Stokes equation is one of the most basic yet the most advanced fluid mechanics governing equation, but still it does not govern the fluid motion completely. Reason being, there are assumptions involved. The assumptions are incompressible fluid, Newtonian fluid, constant properties, mechanical pressure, etc. So, but still, when we apply Navier-Stokes equation to various problems, we actually simplify it. And how do we simplify it? We simplify it by making certain more assumptions, because it's not easy to solve this equation because there is a non-linear term here. So what do? Our target first is to non-dimensionalize this equation. So this is the continuity equation, incompressible flow, and same assumptions again. So while non-dimensionalizing, we need some parameters to which we will non-dimensionalize it: the characteristic length, the characteristic speed, the frequency, the pressure difference, and the gravitational acceleration. So these are the non-dimensional terms that we have got using the scaling values. So when we will put this in the continuity equation, we will get our non-dimensionalized continuity equation. It's almost the same, nothing typical. But when we will put this into our Navier-Stokes equation, then and after some mathematical calculation, we will get this equation. This is the non-dimensionalized Navier-Stokes equation. So here what we can do now, we can play with things. So there are three important, although Strouhal number is responsible for some vortex trading thing, but Euler number one can easily see. This is the Froude number, this is the Reynolds number. So Reynolds number is a ratio of inertia forces to viscous forces. Froude numbers gives an idea of the gravitational forces, inertia forces, and gravitational forces. Euler number has other significance. So we can get an idea how to and which terms we can neglect in order to move forward. So for example, like in fluid statics, so what's the thing there? In fluid static there is almost no motion, so this term is almost not utilized. The gravity is there, okay, because there is no motion, so the viscous term is also almost zero. So the pressure and the gravity forces, these forces are dominating. Thus the equation just simply reduced to this simple equation, no non-linear term. So what we are doing here, we are making certain good approximations, and we are reducing this complex Navier-Stokes equation, which is a very good governing equation for fluid behavior. But although it also comes with lot of assumptions that we need to be very careful. For example, in this case, this is a very good example. Here we can see this is the fluid static region that we just saw, where the pressure and gravity forces are more pronounced, and this small region, this is the rotational flow. So in a specific problem itself, lot of regions, and region wise the problems can be different. So there is in creeping flow, the Reynolds number is less than 1, means the viscous forces are always greater than the inertia forces. In inviscid or rotational flow, inertia terms dominate and viscous forces are almost not there. But the boundary layer thing, this is different. Here what happens, away from wall it's like potential flow, and near the wall the viscous flow are dominating, like creeping flow. So what happened around late 1800s, the problem was that these people mathematically, analytically, these viscous problems could also be solved, the potential problem could also be solved, but in real life situation always the structure interacts with the fluid. So what happened, uh, a German scientist named Ludwig Prandtl gave a very nice theory in 1904. This theory changed everything in fluid mechanics. Here broke he what to say he uh, divided the flow into two parts. He divided the flow into two parts. One part which is the part where the potential flow is there, and another part where the flow is viscous. And this theory was very remarkable, and we will see how. So what happened actually, let me, these three people are his students. Almost everyone is German, but this fellow, this guy, Theodor von Karman, during World War he went to the States. So boundary layer theory was applied in this warfare also. One, and on both the sides, on the NATO side, and these people were on the almost on the German side. So research needs funding, sometime war provides it. So let me just give a very basic idea. So if this is a, let me assume that this is a airfoil. Flow is happening. So due to no slip condition, fluid will be sticking on the surface. But in free stream velocity, there would be a free stream velocity. So this layer, this boundary layer will be formed. This boundary layer is the separation between these two. This is what Prandtl told. Just to separate these two flows, he hypothesized a layer which is a boundary between these two regions. So because of no slip condition, there is an area where the velocity changes, and this gives the characteristic velocity profiles that we are drawing always. So what happens, because the lower region, this is not equal to 0, this profile is not uniform, so shear stress is there, because tau is equal to mu du by dy, but here this is uniform, so shear stress is 0. So this is a non-viscous region and this is a viscous region, and because Bernoulli equation or the classical Bernoulli equation does not provide for any losses, so Bernoulli equation holds in only the irrotational region but not in the boundary layer region, although if we put losses we can use it. And the thickness of the boundary layer is defined as the location where the error in the measurement is 1%. So usually it is taken 0.99% of the free stream velocity. Wherever this condition is reached, or almost the velocity becomes constant while measuring, the velocity almost become constant around 1% error. So it is said that this is the boundary layer thickness. So now for boundary layer, when we see the equations, what is we, because for this also, for every situation we need to do a dimensional analysis. So here also we have taken some scales. U free stream velocity for the velocity, this rho u square for the pressure difference, the L is the length scale, and the delta is the length scale in y direction. So when we put this in the continuity equation, we will get an idea about the scale of V, because V we were not able to get, so we get the order of magnitude of V. Now we are putting this order of magnitude in V. And then when we put these things into the y momentum equation and do little calculations, we get this equation. Now what is the thing that always the Reynolds number is very high for boundary layer. The boundary layer thickness is very small, and here one assumption is that the Reynolds number is very high. So these two things are the inverse of Reynolds number, and Reynolds number is very high. So these two terms cancel off, and this pressure term remains, and we will find out that the order of magnitude of this pressure term del P by del Y is almost zero. What does this mean? This thing means that when the pressure in the y direction, this is the boundary layer coordinate system, the y is always perpendicular or orthogonal to the surface, and the x direction continuously changes with the surface. This is the boundary layer Cartesian system. So this means that when inside the boundary layer the pressure is always same in the y direction. And this is a very important thing because it has very good consequences. So whenever we are having or measuring any tappings, whether maybe it is a venturi or an orifice meter, we always tap on the walls. So due to this consequence of boundary layer, because there is always a very thin boundary layer, we will always get the pressure, we will always get the static pressure at the walls. So because now we have seen that this P is not changing with Y, so only X is remaining, so we can change this partial derivative to a normal derivative del P by del Y to dP by dx. When we put this in our equation, we get this dP by dx, and further when we non-dimensionalize this equation and we multiply with L by U square, so we get these things. Now same thing, because Reynolds number is high, this is not there, so this term also becomes 0. And when this term becomes 0, so what is the thing that is happening? The order of magnitude of this and this is 1. So we can equate this thing with 1, and when we do this, we get a very interesting thing. We get Reynolds number, and when we get Reynolds number, we get that del by L is inversely proportional to the under root of Reynolds number, and this we can extend for X also. By changing L to X, for local Reynolds number, we can get the thickness of boundary layer at any point, and it turns out that the thickness of the boundary layer is proportional to the square root of the location of X. So finally what we get, two things: P is only the function of X, as U is also a function of X, delta is also some function of X. These things are there. These are our boundary layer equations. So one very important thing here, that Navier-Stokes equations are elliptic in nature, which means they need data from all the sides. But because the x momentum equation of boundary layer is parabolic, it requires only 3 sides. So we can give it the top side, we know, the bottom side no slip condition, and this side we also know. So it becomes very easy for calculation and for computational calculations, because the third or the downstream needs no calculation. You can simply mark downstream and you will get the values. As the flow increases, as we go deep into the as the length increases, the boundary layer increases, and you see that these profiles, first it was like this, then it's like this, then it's like this. So the value as x increases, del u by del x and del u by del y is also increasing. Means, what does it mean? It means the shear stress is reducing. It should increase. Okay, the profile is changing, and let us see. This is the delta value, and the same thing. The profile is changing. We will see what is happening here. So this is what actually Blasius did. I am very sorry. Blasius found a very, he is also one of the students of Prandtl. what he said that along the profile, along the length of the plate, this profile is actually changing. But he pointed out that all these profiles are same, because as the length increases, two things happen. This is here wide, and later on what happens, it becomes thinner and it becomes taller, because this layer is growing, so it becomes tall and it will become thin, and here it will be little fat and it will be small. So what he said that these all are similar and they have a similar profile, and in short what he did, he non-dimensionalized this velocity profile and showed that everything changes with x only. With there were two parameters, y was also there, this y length was increasing, y was increasing. What he said that with increase in x, this profile is also changing. So he simply non-dimensionalized this with eta. So this will be the profile always. It will stretch little or it will compress little. That's what said here. So that is what Blasius did. This is known as the similarity solution. I'm not going to great details in Blasius solution, but this is the thing. Now, very important consequence of boundary layer theory is the entrance region. So what happens if there is a pipe and flow is happening inside this pipe? So boundary layer is developing on both the directions. So what is happening, that initially this profile is uniform, but slowly when it progresses, this region is boundary region and this is the uniform part. So what happens, up to a limit these things develop, there are changes, but after some time these profiles are exactly same. They are exactly same. So this region where the profiles are exactly same is known as fully developed region, and this region is known as hydrodynamic entrance length. This entrance length is more important when the length of the pipe is small, and when the length of pipe is huge it really makes a difference, but for small length pipe it is important to understand. Next, shear stress. So what is happening here, you see here, because it's entering this sigma value here, initially this the profile, it's little having small slope, greater slope, and here later the slope decreases because it's becoming fuller. So here it is less steep, here this is more steep. So del u by del y is more here and del u by del y is less here. So shear stress is more here on this location. So what happens, initially in this area the maximum shear stress is at this location, but it becomes constant here. That is what we can see here in this lower diagram, that this is the peak of shear stress, and after this the shear stress is almost same. So during the maximum shear stress undertakes at the entry of the pipe. So this is the same thing, increase of shear stress in x direction. So this is a plate and it is in a uniform flow field, and some ionization method they are visualizing the flow, and slowly this, you see, in the beginning this profile is having greater angle, that is what I told, and later this is decreasing. So the shear stress initially is greater than the shear stress that happened later. So more shear stress is in the beginning. So what is displacement thickness? So actually displacement thickness, hypothetically speaking, if there would have been no wall, so the streamlines would have passed without any interruption. But what is the distance which the streamlines are disturbed, the distance up to which the streamlines are disturbed or moved because of the presence of the surface, that is the displacement thickness in its essence. And what is the momentum thickness? Momentum thickness is the amount of it is the distance in the direction perpendicular to the wall surface up to which, if the flow field is lifted, then the momentum loss, because see there is a moment of diffusion happening, so momentum is getting diffused from top to bottom, so there is a loss of momentum. So this thing that is happening, we are just quantifying it, that how much distance, if the layer is uninterrupted, then the momentum that was lost can be regained. That is the momentum thickness. But this boundary layer uh, phenomena, it's not limited to only flows. There we were talking about momentum diffusion. Here we are talking about, in thermal boundary layer, we are talking about thermal diffusion. So the same way, if the plate is hot, here in this case the plate is cool, so the temperature at the plate side is less, and at the free stream this will increase. So this is the thermal boundary layer. So what's happening? See, now when there are two things, then there will be a comparison. So this is the momentum thickness, so it's like this, and this is the thermal boundary layer. So how you will know which one is greater? So there comes some parameters, Prandtl number, named after Ludwig Prandtl. So this is the thermal diffusivity, this is the momentum diffusivity. So this is the ratio. If diffusion of momentum is more, so the momentum will go higher. So in this case, see, momentum is not getting diffused too much, it's less. Diffusion of momentum is less, and diffusion of temperature is more, heat is getting diffused easily, so the bottom term is greater. So Prandtl number here would be less than 1. So for air Prandtl number is roughly around 0.7, and for oils and other things it is around 10 to 100 and these kind of things. So for oils, what we get to know, that for oils momentum diffusion is happening quickly and heat diffusion is difficult, but for air it's the other way around. So see, these are the two cases. Prandtl number is less than 1 means this thing is greater. Momentum, molecular diffusion of heat. Heat diffusion is fast. So heat diffusion is fast, so thermal boundary layer is greater. Thermal boundary layer is greater, and this momentum boundary layer, this is small because Prandtl number is smaller than 1. This is the case of things like air. Prandtl number is greater, this for oils and lubricants can range up to 100, sometimes I don't know, around 100. So here what's happening, because Prandtl number is greater, so molecular diffusion of momentum is easy. So momentum boundary layer is big and thermal boundary layer is low. So these are oil kind of things, these are air kind of things. So this is thermal boundary layer and its comparison with the momentum boundary layer. So same thing in entrance length. If entrance length, there is a thermal entrance length and there is a hydrodynamic entrance length. So if Prandtl number is less than 1 means molecular diffusion is great. So this thermal molecular diffusion is great. So Prandtl number is less than 1, so this is greater. The bottom one is greater. Momentum diffusion of heat, molecular diffusion of heat is more, so thermal boundary layer is bigger, so it will form quickly. Xt is small, and because this is forming slowly, so this will come later. And similar case for Prandtl number greater than 1, and there can lot many things can happen. If it's other case, here this is forming delayed, you heat it here, uniform heat flux, uniform heat temperature, so you can play with it. There are many cases here, special cases, you can play with them. So what is turbulent boundary layer? So what happens, up to, there are two limits, there is a lower limit and there is an upper limit for this transition. And on flat plate, usually what happens, that always happens, that everything is laminar, then there comes a transition and things become turbulent and there chaos happens. But what happens, that practically somehow near or even lesser than this value, this transition happens. And you never know if transition will happen here or here or here or here or here. Sometimes this turbulent flow, it is not required or it's undesirable. Sometimes it's desirable. So this equation, these diagrams are not to scale. These boundary layers are not that big. They are very thin. This is also not to scale, but lengthwise you see laminar region is very less. Then this much amount of surface, this is medium, is transitional, and then transition. So in regions where you need turbulence, right, for heat mixing, for conduction, sometimes you have to break the sublayer to enhance the heat transfer. So this transition area is too much. So to get little clarity, what people do, they put some tips wire. They induce turbulence. So you with sudden increase, you know that okay, turbulent flow you have started. These kind of things people do. What happens is now there are profiles. For laminar, you see there is a del u by del y value for laminar, and there is a del u by del y value for turbulent. So here we can easily get that state space is more in case of turbulence because of the way these profiles behave. And we will see more later. One very important thing about this turbulent boundary layer is that there is a very thin laminar layer always present inside, which is known as the laminar sublayer. And how you can know, because see in this laminar layer you see this profile is straight for this much region, in turbulent flow there is a very small area where this is linear, so that shows the laminar sublayer area, and that is sometimes what people have to do if you want heat transfer to take place in this direction. So this laminar sublayer, because molecular diffusion is happening there, turbulent diffusion is not happening there, so it restricts the flow of heat. So what people will do, people will put some ribs sort of thing, and they will just distort this laminar sublayer just to enhance the heat transfer. So this is a log plot. So what's happening, the thing that is logarithmic, that becomes straight line, this log region, this becomes straight line, and the thing which was straight line initially, that becomes sort of a curve. So what is happening here, one very important figure here is this is 5, 1 2 3 4 5, sorry, this is 5, this is 5, and here 11 or some value here, something 11 like this is another thing. So this is the viscous sublayer region, and this is a non-dimensional scale. So up till here y plus something is called y plus value is around 5, and here y plus value is around 11 point something. So near to the surface of wall there is a very small laminar layer, and later everything becomes logarithmic. You can see the profile of laminar turbulent flow is logarithmic in nature. So this logarithmic when plotted behavior when plotted on a log plot comes as straight line, and this is the region which is called the buffer, where these two things are interchanging. This phenomena is very important for CFD and treating the wall, how to, because the interaction between the fluid and wall, it is very important. So when modeling fluid flow, while making grid and understanding the grids, it's very important. So just to capture the behavior at wall, what people do, that they make finer grid, because these are data points. Wherever you will take data points, if I will simply take a data point over here, it will just make a straight profile, but we know that there is some sort of curvature. So to capture this curvature, we have to put lot of data points here. So while making a decision that how much far should be the first data point from the surface, this log behavior is very important. See, this is a aerofoil, 2D mesh of aerofoil. At the surface, you see the thickness of meshing is very thin. This is just to get see, now there are two ways of doing this. There is a way that is known as resolved mesh, and there is one way that is known as wall function. So while modeling, if the first, what we should always try to do, that we should always place our elements inside here. If we are placing our first element or at least two elements here in this region, if we are putting in this region, that it is called as a resolved mesh. And if we are putting it in this region, then it's known as a wall function type of thing. But we should never keep it in the buffer region, because buffer region, no one knows what's happening there. So either you resolve the mesh, either you, this is a example of a resolved mesh. This is an example of a resolved mesh, and this is, and how people are using this wall thing, because there is a great guy known as Spalding. He made a great fit for this, although at the end this overshoots. But this approximation has been made with experimentations and with DNS simulations also. But what is the problem with this thing is that it is only applicable where pressure gradients are not there, infinitely flat plate is there. So there are a lot of assumptions. So one needs to justify by using these equations. This now, boundary layer separation. This is very important thing. What happens actually, that to stick, because there is a momentum transfer. So if the fluid is not having enough energy, so it leaves the surface. And how and where you find that it's leaving, the basic thing is adverse gradient. See, in this region, del P by del X is small. This means that the pressure is reducing as X is increasing. So pressure is reducing. What will happen when pressure will reduce? If the height is almost fixed, velocity will increase. Okay, what will happen if dP is greater than 0? Pressure is increasing, so velocity will decrease. This is known as adverse pressure gradient, because velocity is slowing down. At some point of time, just after this, the flow will go on the back side, because this is adverse gradient. Here at this point, this is greater than 0, this is less than 0. There will be a point where shear stress will be equal to 0. Sometimes we check with the profile, and why it will be 0? Because del U by del Y at wall will be equal to 0, and that point separation will take place, and this is the cause for positive pressure gradient. Positive pressure gradient is the cause for flow separation. And when this happens, when there is a curvature, you see this backflow is happening. So this is not desirable in some cases, this separation. So there is separation control. One very good basic thing, if the boundary is the body is also moving with the flow, so separation will not take place, because it is not retarding it, it's forcing it. But on the other direction, some other thing is happening. This gives rise to Magnus effect and other things. So there is some sort of lift is generated, because see, there is pressure, because velocity is less here, so pressure will increase here, and because velocity of flow is more here, so pressure is less, so obviously a lift force will generate. And these forces, in cricket there is in swing, out swing. In football, people will kick in rotating direction and the ball will curve. And top spin, in tennis there is top spin, there is chop, all those things, all those mechanisms, that is due to this thing only. And this separation thing is a cause for lift. Another thing what people have done, you just, if pressure P1 is here and pressure P2 is here, P1 you reduce than P2, so there is a suction here, so it is sticking the surface, so it is trying to take out the less energy fluid flow, so that the higher energy fluid flow, if this is the profile, so it's just grabbing this less low energy flow and it is sucking inside. But if this kind of thing is employed, So what will happen, that you are also giving power if you are reducing this drag, because this separation is not happening. If separation would have happened like this, so this will be a low pressure region and this would be high pressure region, because flow is greater, so the pressure is here low, velocity is more here, so pressure will be low, and velocity is less here, so pressure will be more. And if this thing is moving is in this direction, so drag will happen. If the separation area is too much, why cars are streamlined? If separation is too much, so there will be a pull in this direction, because there is a negative pressure here. There will be a pull, and there is there will be a pull in backward. But if we reduce this separation area somehow, so the drag reduces. Some other methods, you can inject high speed flow inside here, so the low energy flow is replaced by high energy fluid, and you can suck inside this the low energy thing. Another thing that was there was a porous medium. You can have porous medium and you can continuously suck out the low energy waves. And this is another thing, you can use some jet sort of thing just to increase. If the separation would have happened here without any external force, so the separation will happen later at some place, so you are reducing the separation. Always separation when the divergence is taking place, because see here the velocity is in this area velocity is decreasing, so there will be adverse pressure gradient. This is the reason why when divergent channels are made, this angle is always less. If this is alpha 2 and this is alpha 1, so alpha 2 will always be less than alpha 1, so that these things don't happen. This is one also very good example of separation control. See, this is normal flow is happening here. Now in the next slide, what they have done, these two things are causing negative pressure, so they are stopping flow from separating on this side. Later what they have done, they have started giving negative pressure on this side, so they have controlled the separation is not taking place. Now in a venturi tube, what happens, see what I told, this angle is always less than alpha 1, this angle is small. This is because to avoid, because there is unfavorable pressure gradient, but to reduce that unfavorability so that the flow does not separate. See, this is a divergent channel with a small angle. This is a divergent channel with a small angle. Flow is taking place. No separation, because this is adverse pressure gradients are there, but they are not that adverse that the flow is reversing. Now the same, with the same velocity, the angle is increased. You see this, the separation is taking place here. You see the flow profile, the separation is taking place here. In a more magnified view, see this separation is taking place, flow is going back. So this separation should not take place. That is why if this angle would have been little less, the separation we could have avoided, or if the velocity is low. And see what they have done here, they have added a tripwire here, so they have made this turbulent. So what is the feature of turbulent? When flow becomes turbulent, it is easily diffuses momentum. So when momentum is diffused easily, you see that on the top wall separation has happened here, but here separation has happened here. So this is using turbulence. Sometimes it may be favorable to do this, but usually in aerodynamics people avoid. Now airfoil is there, this is a uniform flow. If the angle of attack we slowly change, separation start happen on the top surface. When separation is happening, see flow is velocity here is great, so pressure velocity here is low, because okay it will be low because it will slow down here, so velocity will be low, so pressure will be high. And here velocity is high because no constraining is there, so pressure will be low, so a lift will be generated. And this situation where the flow is completely separated is known as stalling. Stalling is the maximum uh, lift condition. It happens around 10 to 15 degrees. And drag, one very important thing in drag is usually the flow is laminar. See, for every structure there is two regime. For golf ball this is the laminar regime and this is the turbulent regime. So for laminar regime the drag is high and the turbulent regime it drops, but usually the flow is low. But for a smooth sphere, for turbulent regime the drag is low. So this is kind of interesting, one can see. Now boundary layer are not only the boundary layer that we saw, they can be very, because they can be seen in different fashions also. If a jet is happening and this is a quiescent flow, it's almost stationary, u is almost 0, so here the velocity is 0 and then there is a boundary layer. Another case is that when jet is, that we already saw, u is here 0 and it's there, so this is another kind of boundary layer theorem. And if see some, this is wakes, not jets, this is wakes. If a structure is there, flow is happening around, so flow will try to come back in this direction. So this is the boundary layer thing where the profiles are matching. It can be defined in such a way. Another is mixing. If there is a slit here, u, there is u is 5 here and u velocity here is 15, so there will be a region where this will be mixing. So this is mixing, this is mixing. So you can define the boundary layer like this. It's not always like that wall thing, it can be different. These were the references for the theory. Now let's come to the lab demonstration. We will do a very simple experiment in a lab just to see how this boundary layer develops. So this is a schematic of a wind tunnel. So this is the settling chamber that makes the flow uniform, and this is the contraction, and this is the test section. It's not completely uniform. Near the wall there will be a little boundary layer thickness, and this is the diffuser. So you see the angle here is very less. This is our setup, and what we will do here, this is the settling chamber, this is the settling chamber. There are baffles in this so that the flow remains uniform. What we will do here, we will put a little plate and we will try to measure the velocity at different y locations using a pitot tube. What this pitot tube is doing, pitot tube can move in the x and y direction. We can fix it in the x direction, we can move y, and we have a screw sort of mechanism, so that we, because the boundary layer is very thin, so we need very precise measurements. So, and what we will do, we will just change the y locations and take some readings inside this boundary layer. And because this thing is very small, that is why we need precise measurements. We will fix the location of x maybe at one place and two place, and we will change the location of pitot tube to get various velocities. There will be some differential pressure measurement setup that I'll explain. So this is the tapping for static pressure and this is for dynamic pressure, and we will have, this is the sharp edged plate. This edge is sharp, you know, blunt plate will not work, it has to be sharp. Otherwise, if the plate would be blunt, it will not be boundary layer, that will be something else. This is the pitot tube, stick to the wall right now. This is dynamic pressure connection, this is static pressure connection. Now what I'll show is how, using this screw attachment, we will take very sensitive readings, because with one rotation this thing will move 1 mm and there are 10 markings, so we have a least count of around 0.1 mm. So with an accuracy of 0.1 mm we can measure the y motion in the y direction. This is the differential pressure measurement equipment. So what is here, we have the manometric fluid used here is diesel. It has a specific gravity about less than half of water, so that it can be little sensitive. These are the different heights, And I've shown this connection in such a way because these tubes, how they are connected, it's difficult to see in images. So this is a schematic accordingly. So the dynamic pressure connection, the right side one here is connected to the pitot tube, the left side connection is connected with the static connection, and you will be given data in this kind of form. This R thing, the correction factor, the correction factor is nothing because when the pitot tube is there, some deflection in the streamline takes place. So for correction, the supplier has given some correction factor. So here you will get the head values h1 h2 in centimeters, then at a fixed position or at multiple position you will get the x values, and the y values slowly it will increase, and you will get a corrected y values. So what is there? H1 H2 are measured, x1 is measured, y is measured. You have to calculate u, ux and h. These are the values given for the calculation. You have to give an output in this sort of table. You have to first calculate h values and then you have to calculate the u values. For h, this is the formula, this is the manometric fluid and this is the density of air. You can just simply put it. And this is the Torricelli equation. You put the manometric head here and you put the CV value and you will get the ux value. If everything goes well, you would get a profile like this. Because it's not very accurate, some profile like this you will get. Thank you.